Alright, now we're going to relate all of the graphs that we've done so far and add one final graph to the mix, the acceleration versus time graph. And these tend to be the most crazy looking graphs, I would say. They don't have much of a curve or anything to them. Alright, so what we want to talk about, I think, should be a constant velocity motion. Alright, an object is moving with a constant velocity, which means that it must be moving along a straight line, and the velocity has to be in the same direction as the motion of the object. Alright, so let's see if we can figure out what the graphs would look like for something like that. Okay, well, remembering that the average acceleration is equal to the change in velocity over the change in time, and we said that these graphs are going to be for constant velocity. If the velocity is constant, then there's no change in velocity, which means the acceleration has to be 0. So we'll call this our 0 line. Alright, and we'll go ahead and call this our 0 line for all of these graphs. So the velocity, if the velocity is constant, and let's say that it's positive velocity moving in the positive x direction, then the graph would look like that. And then our position would have to be a positive slope, alright? And notice it is linear, it's a straight line, or as straight as I could draw it. So that's a straight line. Remember that the slope of a position versus time graph is the velocity. So the slope of this line here shows us a constant velocity. This velocity here is above 0, so it's a positive velocity, which means we have to have a positive slope over here. Okay? You could also have a constant velocity of 0, which means that your position has to be 0 as well. Okay, the object is at rest, it's not moving. So since it's not changing position at all, then the velocity is not changing at all, and the acceleration is still 0. The acceleration is going to be 0 for all of these because the velocity is constant for each of the graphs. Okay, we could have a final situation in which we have a negative constant velocity. And if you have a negative constant velocity, then you have to have a negative slope for your position. Alright, it's linear, which means that the velocity is constant, and the direction of this line is negative. It's below the 0 axis, so that gives us a negative velocity. So we have this negative velocity here, which is constant, which gives us a 0 acceleration. Alright, so for constant accelerated motion, we could have a positive acceleration, we could have a 0 constant acceleration, we could have a negative constant acceleration. I'm trying to make those as horizontal as I possibly can here. Alright, if you have, let's say, a positive acceleration, then your velocity graph, remember the slope on a velocity graph is the acceleration. So if we have a positive acceleration, then we need to have a positive slope over here. Now your velocity could start out positive, it could start out at 0, or you could start out with a negative velocity and then become more positive. So if you have a positive velocity, then that means that your position versus time graph has to have an upward curving slope. So you could have something like this, or maybe that, or even something like that. Any of those would work as a upward curving slope there. Alright, so what if our acceleration is a constant negative value? Well, on your velocity versus time graph, you need to have a downward facing slope. So depending on where your velocity originally started from, you could get any of those lines. And if your velocity is a downward facing slope, meaning it's getting more and more negative, then you need to have a downward facing curve on your position versus time graph. So you could have something like this, or you could have something like this, or something like that. Any kind of downward facing curve. If you have acceleration equal to 0, then that just reverts back to what we looked at for constant velocity motion a minute ago, where we had a velocity, a positive one or a 0 or a negative, and then we could have linear in the positive direction or the negative direction or at 0. So that's something we've actually already looked at. Alright, so here we have an example of an acceleration versus time graph where we have a positive constant acceleration, and then we have a negative one and a positive one, and then one here at 0. Alright, so this corresponds to something we've already seen. So if you have an acceleration that's equal to 0.4 meters per second squared, then that means that if you were to look at a velocity versus time graph, that the slope of that line, remember that the slope on a velocity versus time graph is the acceleration, that the slope of that line has to be 0.4 meters per second. So like if you plotted this point, and then you did your rise over run, then the slope of your line would have to equal 0.4. And if that would correspond to this acceleration right here. Alright? And then if we extended that out, and look down here, all of a sudden the acceleration changes to negative 0.4. So that means you're on your velocity versus time graph, then your graph would suddenly start doing something like this. And if you plotted these points and again did your rise over run, then your slope would be the negative 0.4. And then you could continue and jump up here to 1.2, and so your graph over here, this might be a little difficult, your graph would need to jump up and have this straight. It's not going to let me do it. It's going to have this upward positive slope here, and it would need to be steeper than the angle here, or here. So you would take 2 points and plot those, and then again do your rise over your run and get your value of 1.2 meters per second. Alright, and then finally your acceleration here is 0, and so on your velocity versus time graph, you need to have a 0 slope, which means that it would have a straight line at that point. Alright, so that if you plot any 2 points along this path here, the slope is going to be 0. So you'll get that 0 piece over here. Alright, so one final property here of the acceleration versus time graph is that the area under the curve, or under the line here, is going to be equal to the change in velocity. Alright, so this is going to be change in velocity. So just like on a velocity versus time graph, the area under the line represents the change in displacement. The area under the line on an acceleration versus time graph is the velocity. Okay? So here, if we wanted to find out what this one is, the area under that rectangle is, or of the rectangle, is the base times the height. So the base is 0.5 seconds, and the height is 0.4 meters per second squared. Okay, this second's in the numerator, it cancels one of those seconds, and we are left with 0.2 meters per second. Alright, so this object is traveling at 0.2 meters per second during this time period here. Alright, so if we look at a position versus time graph, then it's going to have to be an upward facing curve. Alright, and the slope of this, let's do from 0 to 0.5, because that's what it shows back over here for the acceleration graph. If we go from 0 to 0.5, and we're looking at these points here, the slope of a position versus time graph is the velocity. Alright, so the slope of this line here would have to equal the 0.2 meters per second that we calculated as the area underneath the acceleration versus time graph. So if you came over here and plotted that and did your rise over run here, then your slope would end up being this 0.2 meters per second. Okay? Alright, I think that's enough for this time, so thank you for learning with me, and I will see you next time.